fun studying these lectures and these contents. Now we are going to discuss and study about the system evolution recommender. So what is system evolution recommender? So for that we'll cover these three of mine paper, that is the system evolution recommender for network reconstruction, and we'll see just abstract of these three papers and for the graph evolution and change learning, and that could help you do the system evolution recommendation. So we'll have this one short paper also for in the ICDM workshop, and one more paper on that system science and cybernetics in 2018. All the two conference paper are on 2018. All of them basically related to graph evolution and change learning, and they have the same objective of doing the system evolution recommender for the system evolution analytics part. So in this, we'll start with the system evolution learning, system graph evolution learning, system evolution recommender, then experiments. So first we have to understand the graph deep learning. So basically deep learning is the predefined notion that actually generates deep neural networks. So I'm not going to explain about this deep learning. So you first go and study about this deep learning from this research paper or some study material, previous study material. Then DNNs are actually deep neural network are said to be good for the deep level learning for classification of the data with a small error rate, means they actually do the prediction and recommendation with a smaller error rate. Then we use the three famous techniques for of deep learning as restricted Boltzmann machine, deep leaf network, and denoising autoencoder. And then these techniques are being helpful for doing the taking input matrix and doing the reconstruction to generate some output matrix. Then what are the definition fundamental things that we proposed? We proposed evolution and change learning that actually helps you do the that system was able to be able to done with the evolution and changes. So the system goes for the many changes and evolution, which depends on time variant data, which actually generates some time variant data that actually have various states in the state series form. So making a computer or a machine capable enough for understanding that evolution over time and that time variant data without doing explicit programming is what we can say as evolution and change learning. So this evolution and change learning, we defined it like this. Then we defined system evolution learning. So it is by default that evolution and changes keeps on happening over time for the evolving system states at various time points. So basically making machine or computer capable for understanding the system evolution without making any explicit programming. Means you don't do the programming, still the machine is capable of understanding what is the evolution based upon some neural network that you can generate. So the graph evolution learning, you can say, as the evolution and changes basically happens on evolving networks. When you do the analysis for evolution and change patterns in the evolving networks, and you are making the machine capable enough for understanding the graph evolution, then without any explicit programming, then you can say it as a graph evolution learning. The same thing, graph evolution learning could be said as network evolution learning, NEL. So the basic algorithm, the most basic algorithm for the whole work could be like this. The system evolution recommender is there, and you have n different states, and you have to do the learning for those n different states. And you had collected these n different states from a repository of an evolving system, and you did the pre-processing of these n plus one states to generate n plus one evolving networks. So en represent evolving networks. Then you converted these evolving networks for n plus one states to some matrices, and these matrices were being analyzed and done for the evolution representation. Means n states out of those n plus 1, you had chosen only n states, and n states was being combined together to create an evolving matrix based upon some evolution representer. Then this evolving matrix was being used for doing the graph evolution learning. So this graph evolution learning was being done over this evolving matrix, and this would actually be done with the help of deep evolution learning. So you just modify and extend that deep learnings to some which can able to understand that evolution learning, and you say it as a deep evolution learning, and you do the take the evolving matrix as input and generate binary graph matrix as output. Then you do the binary matrix classification, means just comparing the binary output matrix with the testing matrix. It is simply we can say that it's like understanding that comparison of the accuracy, precision, recall, and F measure. So this binary matrix would help you do the understanding of that precision, recall, and F measure. So we did this type of evolution learning, system evolution learning, underlying some graph structure was being learned, and based upon some evolution and changes, we specifically said that this system evolution learning that it takes n plus one states as evolving system as input, and then with the help of deep evolution learning, we generated one sysnet sysnn as the output. Then we proposed actually the system evolution recommender to to do the network reconstruction. Then we did the pre-processing for n plus one collection of graphs for various mapping could be done, and the conversion of n plus one graph into some connection matrix, n plus one connection matrix. That these n plus one connection matrix were being used for the training and learning purpose with some graph evolution change learning algorithm that actually takes n different connection matrix as and produce some output matrix. And this GECL was being used for doing the a deep evolution learner DEL that could actually do the matrix reconstruction to generate the deep system neural network, deep SysN, and and that would actually help you generate the net to do the network evolution and change learning. It means GECL may also be referred as network evolution change learning. Then you do the comparison of the output matrix with the testing matrix, the matrix that was not being used for the training, so that you can have fair testing and fair recommendations. Then you have the generation of making machine capable enough. This process will make machine capable enough for doing the evolution analysis and prediction recommendation for the state series that was used for the training purpose without any explicit programming. Then this is the basic block diagram for doing the system evolution recommender, that we had chosen n plus one states as a state series, n plus one state series. Then we did the pre-processing to generate complex network list, and then we did the conversion of these complex network lists to generate the connection matrices. Then we did the testing part of means this connection matrices were gone for the generation of evolving connection matrix, means that evolving matrix that we discussed for the n states. Then these evolving connection matrix goes to the deep evolution learning along with zero matrix. What is zero matrix? It is basically representer of zero matrix to the zero vector, and this zero vector and this evolving connection matrix goes for the deep evolution learning, and this will generate deep system neural network that will actually helps you do generation for the output vector that could be generate converted to the output matrix M0 MO, and that would be further normalized to do the probability prediction for the binary classification of precision, recall, F measure, and accuracy, with the one remaining matrix that could be used for the testing. That one matrix that you haven't used uh, for the training purpose. So you compare both these matrix and you generate the binary classification. So this is the basic system evolution recommender algorithm, that it takes repository as input, and that actually contains n plus one states, and you generate the list of n plus 1 is adjacency list and mapping after pre-processing. Then this adjacency list was being converted to the matrix of n plus 1. Then graph evolution change learning was being done over this matrix, and this MNO was being generated. MNO was being compared with matrix, and you generate the time series for the prediction purpose. Then what are the remodeling of equation that we did in the this research work is like RPM equation was being modified like and converted to this. So this ECGJK is representing that connection between the entities. So entity connections for the jth and kth. So jth would actually represent some parameters, and k would represent some parameters in the whole thing in the between the various versions and various stages. So you'll go and read about this information in more detail. And this was the DBN, that ECMH, and this the reconstruction formula was being modified like this, and we have this type of information generation for this DBN was being the equation was being modified like this. Then autoencoder equation was being modified, remodeled like this, and we use this evolving connection uh, dependency for the jth and kth parameters. So this is how you can go and study these things in detail if you want. Then we actually implemented this SEL system graph evolution learning type of theory into some Java based tool. And then we did the learning of that evolution and change pattern for from the evolving matrix. And then we actually have that machine enabled with GRE and JDK for that could be of seventh or higher version can manage this tool that actually takes n plus one states of an evolving system, and then do the system graph evolution learning that actually do the two type of learning: evolution and change learning, and graph structure learning. So graph structure learning would actually do the graph train for the n states, and this graph that evolution and change learning was actually being done for the evolution and change training information, and the both the information was being integrated to represent a system's neural network. Then the recommendation system would actually look like this. A recommender system predictions look like this. So this is representing accuracy, precision, F measure, and recall for all the six evolving system. So this is representing Hadoop distributed file system recommendation. First one is for the RPM, second one is for the DPN, third one is for the DA. So these are having four different time series for the accuracy, precision, F measure, and recall. Now just see that the when we keep on having the 15 version training, and the training keeps on improving with the number of versions, and it will do the very good prediction at the end for the testing matrix. Then the similarly for the second row, you can see for the Bible translation, the three different deep learning techniques: RBM, DBN, and DA. And for the different centuries data we collected, so we merged some of the centuries together for the better data analysis. And the again the same four time series: accuracy, precision, F measure, and recall. So the predictions could be done like this: from 0 to 1 means just fraction of a prediction. 1 would represent best, and 0 would represent uh, worst case of prediction. So we got luckily good amount of prediction. But for the precision of the 13 decades of the multi-sports event, we got little average type of prediction, and this would be done for the 13 different decades of multi-sports event. Next, for the frequent market basket. So the prediction would actually depends on how much volatile, how much changing nature of the data was there. So the more changing nature was there, then the lesser amount of prediction would be possible. The higher would be the change, means lesser prediction could be possible. But lesser will be the change. So small changes are there. So better prediction could be done. Means the state one to state two, state two to state three. There is small changes, so it could have better prediction. So the similarly the frequent market basket for the month 12th means December and 10th means 2010. One represent as the January and 11 represent the 2011. Two represent February and 11 represent the 2011. So the whole thing was really presented like this. Next, we got that the information for the uh, positive and negative sentiments of IMDb movie genre system could be look like this. It is also predicting substantially good for the most of the binary matrix parameters, that is accuracy, precision, and recall F measure. So you can see the various decades from 1990s to 1910s to the 2000 to 2010. So 2010 was being used for the training matrix, means testing matrix was being used. So the initial all the starting states are being used for the training, and last state was being used for the testing, and this dotted part was actually representing the prediction recommendation. Then we did the this to do this experiment, we actually do the some aggregation of the uh, three different models, that's RBM, DBN, and DA. We did the aggregation. So what we did for all the all the binary matrix accuracy, precision, F measure, recall, we added up them and divided by 4 so that we'll get average of them. So average binary matrix we defined small change for the theory, and then we represented this average binary matrix as like this. For RBM this would be there, for DBN this would be this, DA this would be represented. For Bible translation, 13 different centuries, multi-sports event 13 different decades, retail market 13 different months, positive sentiments and negative sentiment 16 different decades. So this is how the average binary matrix vary for the three variants of evolving system evolution learning over the six evolving system. So this is how the whole thing would look like. Then what is the advantage and how it would be helpful for the further recommendation of the evolution? It could help you do the prediction between the connections of entities. It is actually helpful for doing the upgrading to the new states. This approach is helpful for doing the intermediate phase system development. This approach would actually help you do the system developers to assist some system developer. Then this approach could help in the speeding up of system development. This approach could be helpful for doing the automated correction of some error during the system development. This would actually be possible future for doing the system analysis part for determining the future of that system. Then what's the conclusion that we actually define system evolution recommender algorithm that actually help you do the internal usage of evolution and change learning. Then we actually process the series of graphs to do the deep evolution learning algorithm. Then we did the used the evolving matrix as input and outputted as sysNN. Then the automated tool was being generated, and we did that tool had did the promising system network reconstruction by doing the and using the matrix reconstruction property of deep learning. So we did the remodeling of deep learning to do the network reconstruction. And this actually demonstrated some intelligent recommendation tool for the three different variants of system learning based upon RBM, DBN, and DA. Thanks. So we'll discuss the next service evolution analytics approach in the next part.